Part 3. Okay, what are we doing? We started with the 2014 calculus equation sheet, and then we found out that the A's were A-OK. Integrals undo differentiation, that's something else we found out, just like logarithms undo exponents, and the power rule cannot handle 1 over x, but that is not a problem. What about these guys? That's what we're doing right now, but first something else. Ah, no, not this guy again. Wait a minute. What if A was -1? What would happen then? What would your slope be? Your slope would be your opposite. So u, your slope, and then your slope's slope is u again, and so on. Get it? Kind of weird, huh? But that brings us to the sine function and the cosine and their derivatives. Sine first. A nice shape. Slope is 1, 0, -1, 0, 1. Cosine next. A familiar shape here. Slope is 0, -0, +0. So we agree. But what about those improved formulas, the ones with the A's? They are a bit odd. A starts out in the angle part of the equation, but it ends up jumping into something that looks like an amplitude. But notice that the A stays the same in the angle part. And that reminds me of, back to the graphs. Sine 2x. Yeah, twice the frequency. I see that now. That would give you a steeper slope. Twice the frequency gives you twice the slope. Sine x over 2, that's 1/2 the slope. Okay. Starting with cosine next, a bigger frequency, a steeper slope, and just one thing. Why did we start with this? Negative, positive, and then we had the sine, slope, 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 and the cosine, slope, slope, slope. Which really, if you think about it, they're the same thing. They get us back to where we started in 4 steps. Can we do something similar to that with e? Yes, we can, with e to the I being the square root of -1. And we did it. We're done, the calculus equations. But wait, there's more to this equation sheet. And once you've mastered the calculus side, you'll recognize this, and that, and the other thing. Yeah, I know I'm going way too fast, but hey, this is an introduction, not a life story. I'm just showing you some of the patterns that you will use and see again and again and again and come to know and love, maybe. But how can integration with the power rule give us equations for circumference, area, and volume? What are we doing here? Are we just following a silly equation, or is there a geometric interpretation? Well, maybe, but first remember this. The function for profits each day, the integral, the area under the curve. I said that gave you the total cash earned. Integration added up all the profits. Integration as the added up function. A fancy sigma, adding up all the money each day applied to circles. S, that's arc length, S equals R times theta, the definition of the radian. ds then would be a small little piece, a tiny little piece of arc length, and there it is. Let's take the integral, adding up all those little ds's, all the way from theta equals 0 to theta equals 2 pi. What's that? That's the circumference, that's 2 pi r. Next, area equals pi r squared. Where did that come from? We'll take the length of this arc, that's 2 pi r. And we will give it a little width, dr. Picture a rope with some width. Or how about instead of drawing a line with a pencil, you're drawing it with a fat Sharpie or something like that. So you're not just drawing a length, but you're covering an area. You're painting a little area with that circle. And add it up with the area taken up by this circle, and this one, and this one, and so on, letting the radius change all the way from 0 to r in little steps of dr. Integration again as the added up function, adding up all these areas, getting pi r squared. And one more to do. Volume as the integral of surface area. Now, showing that 4 pi r squared is the surface area of a sphere, that can be really hard if you do it like Archimedes did it, or if you have the right choice of coordinate systems, that can be easy. That's something we'll do in another lesson. We'll take that as our starting point. Surface area of a sphere is 4 pi r squared. Believe me, next, do it time and time again for each of these shells. Just like those circles, we have shell after shell after shell. Each shell has a thickness of dr. That means each shell has not just a surface area, but a little bit of volume. The integral adds up the volumes, and there you have it, because this equation sheet is not, it looks like it, but it's not just a jumbled mess of incoherent facts. It is an internally consistent system of awesomely useful. And if you can see it here, hopefully you see it there too. Again, not just a bunch of random facts about nature, but a coherent system.